Okay, so black holes are fascinating objects. It was said here many times at this meeting. They are really mysterious. They have certain properties which, in semi-classical limit, you can understand extremely well and even prove. And they are very interesting and look very mysterious. So, for instance, black holes don't have hair, meaning that they don't have memory where they come from. They are only characterized by few numbers, such as masses, angular momentum, and charge, and so on. Then, at the semi-classical level, they exhibit exact thermality of Hawking radiation. So Hawking radiation is exactly thermal, which means that it has no features in which you can store information. They have negative heat capacity, they have Bekenstein entropy, and so on. So this picture sort of pictorially summarizes one of the confusions. This is Alice. She's a semi-classical observer, but she knows quantum field theory. So she's observing a black hole evaporating, and then she sees in the semi-classical limit that the spectrum is exactly thermal. And now, being a quantum field theory person, she wants to understand what is the substance that radiates and has a negative heat. And normally, the first reaction of a quantum field theorist would be that this is some substance in quantum field theoretic substance in thermal equilibrium. But none of them work. As I said, there are other questions. Now, moreover, you can also hook up, build some paradoxes based on these semi-classical observations. Now, for instance, if you take this absence of hair of a black hole, and then there is a small logical gap that normally we fill with an assumption which seems correct and in fact turns out to be totally wrong, you arrive to completely fantastic conclusions, such as, for instance, folk theorems about no global impossibility of global quantum numbers, incompatibility with global quantum numbers with black hole physics, information paradox, and so on. Now, the thing is that the reason why these paradoxes and these puzzles appear because of precisely this small logical gap that we are filling with an assumption. Now, what is the assumption? We assume that big objects, macroscopic objects, are approximately semi-classical. In other words, semi-classical approximation is good if you are thinking about black hole in the center of our galaxy. And that's the whole point. Now, so therefore, once you stay in this semi-classical approximation, in this assumption, these paradoxes are impossible to resolve because they are the artifact of this assumption. So in order to resolve these paradoxes, we need a microscopic quantum theory of a black hole. Okay? And I will try to describe one. Now, here I need to do some, I need to do some clarifications because we have to be extremely rigorous and careful when we define microscopic theory of a black hole. What do we mean under microscopic theory of a black hole? I want to clarify certain concepts because there is often a confusion about them. We sometimes confuse notions of quantum gravity with the notion of ultraviolet completion of gravity at short distances. Sometimes people use these two completely different notions as the same thing. Okay? So normally when we say that we need quantum gravity, we assume that this is quantum gravity at short distances. However, these two are completely different things. So we don't understand completely or what is the UV completion of gravity. We may not understand, let's say, what is the UV completion of gravity at Planckian distances, which is 10 to the minus 33 centimeters. But we understand quantum gravity of 2 gravitons with 1 kilometer wavelength extremely well, okay? We know extremely well how 2 gravitons of 1 kilometer wavelength would scatter. They are extremely weakly interacting, very nice weakly interacting entities. So therefore, this is extremely important to understand that when we talk about quantum gravity, what do we mean under it? What I will mean under this, in this talk, I will assume that I will make an assumption that in order to understand physics of a black hole at the center of our galaxy, I don't have to know what is the UV completion of gravity at 10 to the minus 33 centimeter distances. Now, if you can make an opposite assumption, then, okay, you don't have to follow what I will say. I cannot disprove that, but this is the assumption that follows. Sometimes we call it Wilsonian decoupling in physics, that we understand that in physics of macroscopic big objects should be largely insensitive to the UV completion of theory at short distances. This always works in physics, as far as we know, so we will assume that this is what it works in gravity. So therefore, what I will say will be completely insensitive. You can choose whatever UV completion of gravity you prefer. You can take string theory at 10 to the minus whatever distances, 10 to the minus 30, let's say centimeters, or some other UV completion of gravity at Planckian distances. What I will say will be totally insensitive to that particular theory, okay? So I will be interested in the infrared physics of gravity. And we assume that this infrared physics should be governed by quantum gravity the way we understand it, with gravitons being entities and with their scattering interactions being dictated by the vertices that are coming from Einstein theory, okay? So we are extremely conservative. Now, as we will see, once we take this route, immediately we'll see that actually these no here theorems are simply wrong quantum mechanically. So they are semi-classically correct, but quantum mechanically they are violated. So in particular, black holes could carry happily, there's absolutely no evidence that they cannot carry baryonic charge or leptonic charge and so on. Could even be of astrophysical importance. That part we are still trying to understand. Now, let me explain what is the framework. It's pretty straightforward. Now, what do we know about, first I will discuss aspects which are common for Schwarzschild and Kerr. These both go through. Then I will discuss specifics of Kerr a bit later. Now, Schwarzschild black hole, it comes about as a solution in GR, and we identify it through the metric. Okay, G mu nu is the metric. Now, the moment you say that you identify something with G mu nu, you are in classical physics, because G mu nu is an intrinsically classical entity. It's something that is defined in every space-time point. Okay, so you are in the when we talk about metric, we are. If we make parallel with electrodynamics, we are in the same approximation as when we talk about laser pulse. We use, let's say, classical electromagnetic wave, but in reality, laser pulse is a bunch of photons. So exactly in the same way, we shall assume that the building blocks of the metric are gravitons. Why? Because in quantum field theory, there is nothing else. In quantum field theory, we have a vacuum, which we normally define as state without particles, and then states with occupation number of particles. So, exactly in the same way as laser pulse, classical laser pulse, I can understand as a limit of large occupation number of photons in the laser pulse. We can also understand gravitational wave as large occupation number of gravitons, or a metric as large occupation number of gravitons. Now, the question is, okay, this is perfectly fine. Nobody's gonna probably dispute this, that we can do it. The question is why this is useful. Now, it turns out that for the laser pulse, this is not terribly useful. Okay, in general, if I have a propagating laser pulse and I simply have huge number of photons, I can use classical description, and that would be perfectly fine. It turns out that for the black holes, this makes dramatic difference. And I will explain why this is happening, okay? Now, What is gravity? Quantum mechanically, as I said. Gravity quantum mechanical is a quantum field theory of a particle of spin 2 and mass 0. Now, this particle interacts with scattering, has scattering amplitudes, and the rules we know extremely well. We know that there is a quantum interaction strength which measures the strength of graviton scattering, and this is given by alpha. This is analog of electromagnetic fine structure constant. This is alpha gravity. And alpha gravity is given by h bar times g Newton and inversely proportional to the wavelength of the, or de Broglie wavelength of the momentum transfer of the gravitons participating in the vertex. Okay? Now, notice, this is extremely important. Notice that the gravitational coupling scales as inverse length, inverse wavelength. Okay? So in other words, if I would tell you, take this room and put in this room a bunch of gravitons, approximately of the size of the room, the coupling between these gravitons will scale as not the volume of the room, but as surface. Okay? Now, this will be essentially the reason for holography. This is the quantum, what we claim is that this is the quantum mechanical reason for holography. All these mysteries, this black hole entropy, scales like surface, is originating from this fact, that gravitational coupling of gravitons scales as surface. Okay? Now, then we can define some intrinsically, so it's always good to understand the limits, right? When I'm in quantum mechanics and when the limit to semi-classics is good. So let me define some quantum entities. Now, the quantum entity is the Planck length. So Planck length is just h bar times g Newton. There is corresponding Planck mass, which is inverse to the Planck length, okay, times h bar. Now, in these units, the gravitational coupling constant, you can rewrite very conveniently as the ratio of the Planck length to the wavelength of the graviton. So, notice that this coupling constant literally measures the surface in the Planck surfaces, okay? Literally. Now, once you realize that, then it's not so difficult to imagine that holography is there, okay? Because surface is already here in the gravitational coupling. Now, what is the classical limit? A classical limit is when I take h bar to 0, so in this classical limit, L Planck goes to 0 and alpha gravity goes to 0. Now, let's try to understand from this perspective what the black holes could be, okay? Now, everybody agrees that we can form black holes in pure gravity. Black holes do not require an external source. You can put a bunch of gravitational gravitons together and form a black hole. So you can just scatter gravitational waves. So suppose I ask you to do the following thing, okay? I ask you to take a given wavelength, lambda, much longer than the Planck length, for example, a wavelength comparable with the solar gravitational radius, let's say 3 kilometers, okay? Or the black hole in the center of the galaxy. So I give you a 3 kilometer wavelength and I ask you to put together as many gravitons of that wavelength as possible, okay? Now, two gravitons with the kilometer wavelength, they interact extremely weakly. So the coupling constant, the scattering of graviton-graviton scattering of two gravitons with kilometer wavelength is approximately 10 to the minus 77, okay? That is like a free theory. Essentially, these two gravitons do not see each other. So, the gravitons can notice each other only if you put huge number of them together, okay? If you put huge number of them together, then they start seeing each other because each graviton sees a collective effect from the rest, okay? Now, this means that if I put, in fact, 10 to the 77 gravitons of 1 kilometer wavelength together, then something will happen. Then gravitons would start seeing each other. So what would happen is that each graviton would see a collective effect from the rest, okay? So it's typical Hartree type situation, okay? And then there will be, each graviton will see some collective binding potential and it has kinetic energy. Now you can do equipartitioning. You can say, okay, when I can form an approximate bound state, okay, to the first approximation out of these gravitons. The condition you can rewrite very nicely in this form. So in other words, you see what's happening, that you can form a bound state and self-sustained for arbitrary number of gravitons as long as coupling constant between them is 1 over n. In other words, this means that because, and this is the extremely remarkable property of gravity, which is not exhibited by other interactions. Why? Because gravity can adjust the coupling by changing the wavelength. In other interactions, you have coupling constants which are largely insensitive to the wavelength. But in gravity, you don't. So this means that in gravity, if I give you a given wavelength, you can always choose appropriate number, occupation number of gravitons to form a self-sustained bound state. Now, these bound states have a very remarkable property that they, in this particular case, since here I did not include a net angular momentum, so this is not Kerr yet, I'm talking about Schwarzschild, they become characterized by a single number, n, okay, or which you can translate in favor of mass or the wavelength. So in other words, mass scales as square root of n, the wavelength also scales like square root of n, and the alpha gravity is 1 over n. Now, in particle physics, we call this type of systems large n systems in Toft sense, which means that your system is essentially acquires a new expansion parameter, which is the number of constituents. Of course, not every system is large n. System needs certain very special properties. For instance, this table has many constituents, but if I start expanding properties of this table in 1 over n, it's not terribly useful. So, yeah, this is what I just said. So, this self-sustained bound state is what in the classical limit, if I take classical limit, in which I take h bar to 0, n will go to infinity, r will be fixed, I will recover Schwarzschild. Okay? So, this is a quantum mechanical precursor of Schwarzschild black hole. Now, I am interested in quantum mechanical properties of this object. So, what are the quantum mechanical properties? You can see that this bound state is formed always at the verge of decay. In other words, we call this type of bound states leaky. This bound state is there, but it cannot really hold all its gravitons together. So, bound state is continuously losing gravitons. So, it's like a bucket of water, okay, which leaks and simultaneously melts, so that it's always at the leakage point, okay? And this leakage is a quantum precursor of Hawking radiation. Actually, this is what radiation of the black holes is. Now, how this leakage happens? The way you can think about it is the following, that classically, even if I put a bunch of particles together, this is a Bose-Einstein condensate in a sense, right? So you can never press all the particles in the ground state. There always will be quantum effects which deplete some of the particles, push them to the higher levels. Now, for this bound state, what happens is that there is no high level. They leave the bound state. So once you push particles out, they leave the bound state. So you can estimate this both in using different techniques. Okay, so here I'm giving you very, very simple pictorial combinatorics understanding of this, because what happens is that two of the gravitons must rescatter and one should gain energy above the binding energy, and this gives you a very important equation, how n changes. Now, this equation is what in the semi-classical limit becomes Hawking evaporation equation. But what is very important is this equation that the corrections go as 1 over n. This is extremely important, as I will discuss. Okay? Now, just to illustrate simply that this gives you Hawking evaporation, immediately you can see, you can make the following limit. You can take the following limit. I can define this quantity h bar divided by square root of n times LP. Let me call it T. I'm not telling you anything about what T is. It's just a name, okay? Let me just define. Then I'll take the limit, semi-classical limit. Now, what is semi-classical limit? I take n to infinity, L Planck to 0, but square root of n times L Planck fixed. In other words, I'm taking number of constituents to infinity, but the size of the system I'm keeping fixed, okay? This is precisely the limit in which Hawking did his famous computation, okay? So in that limit, you recover that this depletion equation, all 1 over n corrections vanish because they go to 0 and only leading term survives. And this just becomes a Stefan-Boltzmann law for black hole evaporation. You just recover Hawking. Now, what is the lesson? The lesson is that our perception that black hole evaporation has anything to do with temperature was totally wrong. Temperature of these entities that I'm considering is 0, okay? This is black holes evaporate because of cold depletion, okay? Now, the reason why spectrum looks thermal, because the gravitons that deplete are soft. Now, in other words, what is the thermality in the first approximation? Thermality is about Boltzmann suppression. Okay, it's also about other things, but Boltzmann suppression, right? So you say, I have a source, this source radiates typically in certain wavelengths. Then I observe that short wavelength radiation is exponentially suppressed, okay? So in other words, if I have a huge black hole of the galactic size, mostly it radiates into quanta of the galactic size. Once in a while it can radiate an elephant, but that's an exponentially suppressed process. Now, that exponential suppression you can attribute to Boltzmann thermal suppression, which is also true because in a thermal bath with extremely cold thermal bath to produce an elephant is Boltzmann suppressed. Or to simply fact that constituents are soft. So this is what is happening. The reason why black hole is not producing elephants because you have to combine huge number of gravitons to produce an elephant because each graviton is extremely soft. It's not enough to produce an elephant. So you need a lot of them, and that's an exponential suppression. So in other words, thermality of a black hole in this picture is an optical illusion. In reality, the spectrum is thermal because of combinatorics and because of softness of gravitons. Of course, spectrum does become thermal exactly in the limit in which Hawking computed a thermal spectrum. So everything is recovered. But the question is, what are the corrections? And corrections are not exponentially suppressed. They are 1 over n suppressed. Now, why this? And this is absolutely crucial, okay? In other words, the fact that we see that deviations are 1 over n as opposed to exponent minus n is telling you that these corrections over the lifetime of a black hole are just enough to abolish all these information paradoxes. Because you have to, although correction is 1 over n, you have to wait time of order n 3/2. And of course, these corrections accumulate to something hugely important, 100%. That's why there is no information paradox in this picture. It should not be, of course, we know. Now, with exponential suppression, you would have no chance. If corrections to thermality were exponentially suppressed, you would never recover information from a black hole. So now, the question is, now you should, logically, you should ask me the following question, okay? Because what I'm trying to say that you take a black hole in the middle of the galaxy, which is huge, macroscopic, and by some mysterious reason, I say that the quantum effects for these black holes are important. Now, of course, we suspected that quantum effects for the black holes must be important. Black holes cannot be normal classical objects because they carry entropy, Bekenstein entropy. Normal classical solution should not carry any entropy. But how can that happen? In other words, how can it be the macroscopic object is quantum? Now, this puzzled us for a while, of course. This is what we were getting, but what's going on? Now, this of course contradicts to usual intuition because normally we say that the big macroscopic objects are, in a good approximation, semi-classical. For example, the photon that is traveling from the bulb from the projector to the screen there is a non-zero probability for a photon to virtually decay into a pair of elephant and anti-elephant on its way. There is no problem, you can compute the amplitude of that process. It's there, but it's tremendously suppressed, okay? So we can ignore it safely. Or the same thing, I mean, if you collide a plus and minus with the center of mass energy comparable to the mass of the elephant, you don't produce elephants. You produce very energetic few particles, okay? So there is something special about black holes. They don't behave like normal macroscopic objects. And what is this special? In other words, what we are saying effectively is that if you take a black hole and compare it with an elephant of the same mass, the elephant is much more classical than the black hole. Okay? Black hole is 100% quantum in some respect. Now, to understand this, let me classify certain macroscopic systems. Now, there is a following classification of macroscopic system. Now, universal property of any macroscopic system that we call macroscopic is that they contain large number of constituents. Okay? I call this table classical because it contains huge number of quantum constituents. Okay? However, so in macroscopic objects like a bucket of water, for instance, okay, there is a notion of the number of constituents, but there is no universal coupling. The coupling, quantum coupling between the different parts of the table obeys nearest neighbor rule. Okay? So therefore, there is no universal alpha coupling by which everybody talks to everybody. Then there are macroscopic entities which are one step further. Okay? These are Bose-Einstein condensates. Now, of course, if in this room I put only gravitons or photons of the wavelength comparable to this room, I form Bose-Einstein condensate, then I can define universal coupling constant. Because Bose-Einstein condensates, since de Broglie wavelengths are large, everybody talks to everybody else at the same strength. But still, most of the times, Bose-Einstein condensate would be perfectly classical in long distance description. Okay? So what is happening, it turns out, is that for certain very special systems in which Bose-Einstein condensates are attractive, like gravitons, there is a certain point when your entire macroscopic system becomes quantum. In other words, the system is at the critical point of quantum phase transition. Now, this is an extremely interesting phenomenon of nature on its own. Quantum phase transition means that you have a macroscopic system of arbitrarily large, but the correlations are huge because the entire system is at the critical point. Now, this is precisely condition that I gave you for a black hole. So it turns out that the black holes are just that from the quantum mechanical point of view. Black holes are Bose-Einstein condensates of gravitons right at the critical point. The problem is that they cannot complete the phase transition. They try to complete phase transition, but they cannot because they lose gravitons in the same time and they always are stuck at the critical point. Now, this criticality you can understand in the following way. For instance, if I take a normal Bose-Einstein condensate, we can compute spectrum of excitations above the condensate. So usually we can use approximation which one calls Bogoliubov approximation. So there are certain modes, okay, and typically these modes are spaced. So there is a tower of excitations. So these are collective modes. In the normal condensates, because there is a gap, most of the time you don't excite these excitations. So they are passive. It turns out what is happening is that when you are bringing the system to the critical point, in other words, in the language of gravitons, when you are bringing gravitons to the collapse into a black hole, what we would classically call a black hole, quantum mechanically what is happening is the gravitons are approaching the critical point. In other words, Bogoliubov modes become gapless. So to visualize how dramatic is this, consider a body that you are trying to collapse into a black hole of the, let's say, of the Earth mass or solar mass, okay? So, quantum mechanically, what is happening is that the gravitons that constitute gravitational field of this object, their number is 10 to the 77. And what happens at that point is that they 10 to the 77 Bogoliubov modes become gapless. So all of a sudden, your system, for free, can store enormous amount of information and correspondingly entropy because there is a free degeneracy, okay? This is an extremely special phenomenon. It usually doesn't happen because usually we are here or here. But black holes sit right there. Oh, great. I have 10 minutes. Fantastic. So, okay. And no, this is the point. So this phenomena, we claim, is the key for understanding why black holes have entropy, why the entropy grows with their mass as a surface, okay? Because remember, the number of Bogoliubov modes is exactly n. Now, n was 1 over alpha. Alpha goes like surface. That's why the entropy goes like surface, okay? These Bogoliubov degrees of freedom are actually very nice because you can think about them precisely as these mysterious holographic degrees of freedom, okay? So far nobody managed to identify them, and we explicitly see them. These are Bogoliubov modes. Now, the only thing is that we don't see so far that these Bogoliubov modes are living on a boundary. Their wavelength is comparable to the size of a black hole. The reason why there is an illusion as if they live on the boundary is because of their coupling, because of the coupling going like 1 over alpha, okay? In reality, they don't live on the boundary. They just behave as if they live on the boundary because their number goes as a surface of the system, okay? So this is just mass gap, collapse of the mass gap, what I just said. Actually, I just said this about holographic degrees of freedom. Now let me illustrate by some numerical analysis. This was done by our students for a prototype model of this type that collapses a graviton condensate to the critical point, okay? And okay, you see what is happening here with the energy levels, okay? Energy levels dramatically go down. Now, even more interestingly, there is another signal immediately that your system is becoming quantum. What is here in this plot is one particle entanglement entropy. So you see that there is an extremely sharp rise of one particle entanglement entropy with already number of particles being very few, in fact, like few hundred, okay? So now when the one particle entanglement entropy, in the other words, one graviton entanglement entropy, okay, behaves in this way, you know that your system is quantum, okay? You cannot treat it classically. There is no way to understand this behavior by solving classical equation of motion. In other words, this tells you that the constituents of the system become extremely highly entangled, okay? Quantum mechanically entangled, which is not true for normal systems, okay? Now, yeah, this is also something, I don't know. This is, these are again energy levels, nicer picture, okay? Okay, so now in the remaining 5 minutes or whatever, let me discuss another implication for the baryon number and for Kerr. Now, of course, you can ask this question, why there should be any no-hair theorem? And actually, it's not. So, for instance, if I throw NB number of baryons in a black hole, they continue happily to live in the condensate. An observer that stays outside, but of course, the measurement is suppressed by NB over N. So, in the classical limit, that is true. When I take n to infinity, the hair disappears, and you recover no hair. But it is there. Now, this is the diagram, that quantum mechanical diagram, how Alice can measure the baryonic hair of a baryon, which is in the black hole, okay? There is a non-zero quantum probability for the baryon to rescatter over the condensate, to deplete, and be detected by Alice's probe. Alice is happily outside of a black hole. So in other words, there is no true horizon for finite n. Of course, there is almost like a true horizon because the effects are 1 over n suppressed. So for these 1 over n suppressed effects to become important, you have to wait for a long time. But they are extremely important, okay? And this is the thing. Finally, we are now trying to understand what is happening with the Kerr metric in this situation, okay? Now, 2 of our students, again, are looking at this. So I can just quote one thing because I don't have much time. But it's very interesting that we see that, again, quantum mechanically, the same maximal orbital momentum limit emerges for the black hole, okay? From these purely quantum arguments. You can, of course, once you go to classical limit, you can recover, again, the same story, usual classical story. I can take h bar, I can take this quantity to infinity, and I can have n arbitrarily large. So I can have double scaling limit in which I take h bar to 0, simultaneously n to infinity, and I just recover the normal situation in which G Newton and mass and the orbital momentum are fixed, but n is infinite, okay? So let me now conclude one more thing. Okay, now, of course, there are many implications that this picture, this point of view opens up. First, it is telling us that we don't have to wait for ultraviolet completion at the Planckian scale to understand physics of large black holes. Secondly, the questions are how to use this for the cosmology. Now, universe is almost like a black hole. It's not quite, but it's almost. Because what I mean under this is that if we compute the mass inside the Hubble radius and compare it with the Schwarzschild of that mass, it's the Hubble radius, okay? So in some sense, we are continuously falling, trying to fall into a black hole, gigantic black hole of the size of the Hubble. But if the universe is flat, we actually never make it because we are, the expansion and the expansion compensates. So we always stay at the horizon. So therefore, if I generalize these ideas to cosmology, then okay, we can also think about the dark energy, the gravity created by dark energy as some kind of Bose-Einstein condensate. Of course, things are much less straightforward because this is not an asymptotically flat space on which I can define happily the vacuum, occupation numbers. So the black hole case on the Minkowski space is much cleaner because there are no questions asked. I can define vacuum and build the quantum state. So the outlook is obvious. We are trying to understand what are the implications. And obviously, this framework allows you to address questions that in the standard framework cannot even be formulated. Again, coming back to this information paradox, it's impossible to resolve in the semi-classical picture because it is the result of applying semi-classical picture. So it is exactly the same as why you cannot understand quantum mechanics as corrected classical mechanics. It's exactly the same for black holes. You cannot understand physics of black holes as corrected semi-classical physics. It is intrinsically quantum, okay? And this we should keep in mind. Okay, I finish here.